urban source apportionment of potentially toxic elements in Thessaloniki using Syntrichia-MS biomonitoring and PMF modeling. Our research addresses the critical issue of urban air pollution, specifically focusing on potentially toxic elements, or PTEs, which pose significant threats to both public health and environmental sustainability. The city of Thessaloniki in Greece serves as a pertinent case study, grappling with ongoing air quality challenges, including close scrutiny from the European Union regarding PM10 levels. Traditional air quality monitoring systems, while valuable, often face limitations in terms of cost and the spatial detail they can provide across a large urban area. Therefore, our study set out with clear aims to comprehensively assess Thessaloniki's air quality using Syntrichia-MS as a bioindicator, to quantify 21 different PTEs while mapping their spatiotemporal patterns, to identify key pollution sources using a robust combination of multi-index analysis and PMF modeling, and finally, to establish an important pre-metro baseline for future air quality comparisons. To achieve our research objectives, we implemented a detailed and systematic methodology. We selected Syntrichia-MS as our primary bioindicator, valued for its remarkable adaptability to urban environments and its proven efficiency in sequestering airborne PTEs. Our sampling strategy was extensive, involving the collection of 192 MS samples from 16 strategically chosen urban sites. These locations were carefully selected to represent a diverse range of pollution exposures, including high-traffic motorways, industrial zones, the bustling city center, and the airport vicinity, with samples collected across 3 distinct periods from March to July 2024. Each sample underwent meticulous chemical analysis using ICP-MS to quantify 21 PTEs. We then assessed contamination levels through contamination factor, enrichment factor, and pollution load index calculations, while positive matrix factorization modeling was employed for robust source apportionment, supported by various statistical analyses and meteorological data integration. Our investigation yielded key findings regarding Thessaloniki's air quality dynamics. Temporally, thallium concentration significantly increased 3.5-fold in summer, strongly indicating a rise in traffic emissions, while elements like phosphorus, potassium, and sulfur decreased, reflecting reduced heating. Spatially, location was the dominant factor, with pollution indices confirming severe anthropogenic enrichment in distinct hotspots. Industrial zones showed high iron, manganese, and tin, while traffic corridors had elevated thallium, cerium, and platinum, contributing to an overall strong pollution classification for the city. To understand pollutant origins, advanced source apportionment using PMF modeling successfully identified 3 primary sources. This advanced analysis further confirmed that traffic-related emissions were the most significant contributor at 48%, followed by industrial sources at 35% and crustal material at 17%. Specific elements, which we referred before, were strongly associated with traffic and industrial activities. Crucially, our contamination indices helped refine these PMF outputs, for instance, by confirming titanium's predominantly anthropogenic origin. Multivariate analyses further supported these sources' identifications. Thessaloniki's air quality is predominantly shaped by human impact, with natural sources playing a less significant, though present, role. The Syntrichia-MS effectively traced pollutants back to key urban emitters such as vehicle traffic, diverse industrial activities, and port-related operations, while the city center exhibited a blend of these influences. We also observed clear seasonal shifts in pollution patterns, reflecting changes in human behavior like heating and tourism, alongside meteorological factors such as Saharan dust. Crucially, the strength of our findings comes from an integrated multi-index approach, where contamination indices provided essential real-world validation for our sophisticated source apportionment models, leading to more robust and actionable interpretations relevant to similar urban environments. Our study successfully identified significant anthropogenic sources of potentially toxic elements and their hotspots within Thessaloniki, also revealing distinct seasonal pollution variations. The integrated multi-index approach, combining Syntrichia-MS biomonitoring with robust statistical modeling like PMF, offers a powerful and cost-effective methodological blueprint for comprehensive urban air quality assessment. While we acknowledge limitations such as potential soil influence on certain elemental readings and the current study's temporal scope, these open avenues for future work. We recommend isotopic tracing to further refine source distinctions and advocate for continuous, longer-term monitoring. This will provide even deeper insights and allow for effective tracking of air quality changes, including those resulting from new infrastructure developments like the city's metro system.